Bienvenidos. Ok, estamos siendo grabados. Bienvenidos a todos al tercer día de la segunda Siembra-HoLAGrav Young Frontiers Meeting. Sorry, I have to switch to English. Apologies. So welcome everybody to the third day of this meeting, and we're going to start with the second lecture by Mariana for the next hour. So please, Mariana, go ahead.
Okay, so the plan for this lecture now is to do some actually active research topics. So I'm calling it new explorations in ADS for the double copy. But before we start with the ADS part, I wanted to do a brief review of the first lecture with an explicit example, because we actually need to see how things work to understand what are the issues that can arise in ADS space. Then I'll move on to tell you a bit about what issues happening generally in first space. And I could pick one of either these two topics to tell you about, because I think we'll have enough time for both. And I think I'll go for ADS via correlators, given that this is an active research topic and we still haven't figured out actually how to do a proper double copy. We just understand how to impose color kinematics duality. On the other hand, classical solutions have been understood for 4 years now, which is not that old, but I think it will be more interesting if I show you a current problem for you to solve. So let me start with the short review by doing an example. And if you remember last time, I told you that not only Yang-Mills and gravity have this double copy property, but there's also these scalar fields that are the nonlinear sigma model. And this is a special higher derivative one that's called the special Galileon. So I'm gonna use this example because of course it's way easier to just compute the amplitudes and see everything explicitly for scalar fields. So we're gonna see how squaring a nonlinear sigma model will give you this higher derivative theory. So just to introduce it real quick, we have a nonlinear sigma model of a UN cross UN breaking down to the diagonal UN. And we're only going to consider the leading order term in this expansion, which is known to satisfy the double copy. So its Lagrangian is given by the following, where this is an element of UN, and we can parameterize it in the following way with these bias, and these are just UN generators. So it's a standard parameterization, and there's a lot of parameterizations that you can use, but just for the sake of computations, let's use this one. So let's use just the 4-point amplitude, because that's, again, the easiest and only non-trivial case, because 3-point is very trivial usually, and here you don't even have 3 points. So for the 4-point amplitude, you want a leading order vertex, which is given by the following amplitude. I guess here I call it pi, but I'm calling them phi. So these are phi's, both this phi and this phi. So you have these Lagrangians, you want to compute your 4-point amplitude, and first we're going to compute the partial one, the color ordered. So when this is like trace of A1, A2, A3, and A4. And that's very simple. You just have this interaction with the derivatives. So you have P1 dot P2, but this is going to be cyclic. So you just do a cyclic sum over all the momenta. And you're going to end up with something that looks like S plus U. And as we know, this is related to the T Mendelssohn variable. So there you go. Simple 4-point amplitude. Now, you can literally graph this result and do the double copy very easily by using our KLT formula that I showed you before for 4-point amplitudes. So the double copy will be given by this formula, and here we have this result already. So it's in terms of Mendelssohn variable T. And this different color ordering, if you notice, it's exchanging what we had one for 1 and 2. And T4, we have now 1, 2, and 4, 3. So basically it's exchanging 3 and 4, so it's changing T to U channel. So basically you just change this T for a U and you obtain the other color order amplitude. Plug in here your amplitudes and voila, that's the double copy. Very simple for scalars. And of course, the question will be what that theory is. But before I go to that, let me move on doing the BCJ type of double copy, because KLT was very simple. We were using this trace basis. For the BCJ one, instead, we usually write it in terms of structure constants because we want to have this set of color factors that satisfy our Jacobi relations, as I mentioned last time. So CS plus ET plus EU is going to be equal to 0. And to do that, we're going to change the traces that we had before now for these structure constants. You can use the standard formula for this adjoint representation that we're in. And it's very simple, of course, to just do the algebra and find what the scattering amplitudes will be now. So we want to write it in the BCJ form. So this will be now your BCJ scattering amplitude with the color factor C's given in terms of this. And you can easily compute what each of the kinematic factors would correspond to. But remember, these are not unique. You can have many of them. So this is just one parameterization, if you want, that gives you what will be. This is the full amplitude, so including color. Now, there's an interesting thing that I mentioned last time is that you can relate these kinematic factors that, by the way, you should check easily that satisfy the same algebra. So NS plus NP plus NU is equal to 0. So we have color kinematics duality, of course, in this case. But now let's relate these two different bases. So this color ordered amplitude that I had before can actually be written in terms of these kinematic factors in the following way. So this is something I mentioned in the previous lecture, that there's just going to be factors of plus, minus 1, or 0. So as you can see here, there's no T channel. But if we pick a different ordering, then the T channel will contribute. And the interesting thing about this is that you can rewrite it in a way that makes a lot of the properties of BCJ explicitly. So you can write it in terms of this matrix form, where here I'm choosing as my basis the kinematic factors NS and NU. So the only thing I did is to write NT in terms of the other ones using the fact that they satisfy the color kinematics algebra. And then you can just rewrite this in this special form. So this kind of matrix computation is very useful to understand the double copy. And this is because here we have these partial amplitudes or color order amplitudes, and we know that they are gauge invariant. On the other hand, here we have something that we know is not gauge invariant. So we don't expect a trivial relationship between them. And this matrix over here, in principle, if you could just invert it, you could write this non-gauge invariant term in terms of a gauge invariant thing times some Mendelssohn variables. But one should notice that in this case, this matrix cannot be inverted. And in general, for Yang-Mills and for the nonlinear sigmoid, this should have a rank of n-3 factorial for an AN amplitude. So in our current case, this also only has rank 1. And if you want to do the computation, you will see that that's the case just because S plus T plus U is equal to 0. So this is important, that the fact that this Mendelssohn variable satisfies the relation only in the massless case is what makes this matrix non-trivial. Of course, again, we want it non-trivial because this is not gauge invariant and this is gauge invariant. And the fact that it's non-trivial tells you that there must be some other relationships between these two scattering amplitudes. And surprisingly enough, those are going to be our BCJ relations that we saw yesterday. So if you actually take like this first line of this matrix computation and say you graph and solve for NU, then plug NU back into the second line, you will find the following relation between these two scattering amplitudes. And this relation we saw last time is the BCJ relation. So basically, from the fact that we have the color kinematics algebra, and we can rewrite these amplitudes in this matrix form using the fact that this is satisfied. So color kinematics algebra leads to BCJ relations. So this is very important when we try to understand how to make this work in ADS. So now that we understand how these amplitudes are related, we can just decide to go and find the double copy now in BCJ style, which should give the same result as the KLT. So in BCJ, we square the numerators, the kinematic numerators. So this is just squaring the kinematic numerators, and trivially gives you the same result as KLT. So the question now is, okay, what is the double copy? And in general, if you have a theory that has color kinematics duality, if you've shown it, and it satisfies VCJ relations, we know that we can double copy this theory, and usually, at least in the standard cases, obtain a reasonable theory when you do the double copy. And now the question is how to understand what the double copy is. So you just start looking at features of your scattering amplitudes. So here is a scalar squared, so you're gonna obtain a scalar. So if you look at the amplitudes, you expect a derivatively coupled scalar. And also you can see that they have a sublimit that vanishes like p to the cube. If you just computed higher and higher endpoint amplitudes, you see that that happens for all of them. And also that the sublimit is non-trivial, because here we have a 4-point amplitude, but it's order p to the 6. So you don't have 3 derivatives per field. If you had 3 derivatives per field, then this kind of sublimit will be trivial. So you'll sort of know what kind of theory you have to write. But you know you need something with only 6 derivatives. And magically, it was discovered that this is the correct theory. So this is the so-called special Galileon. And it's just a scalar field that has this derivative interaction. It has some special shift symmetries, and it comes out in a lot of interesting places from brain constructions, but I'm not gonna go into that here. But you can just assume, okay, this is my theory. It actually has second order equations of motion, even though it has these weird derivative interactions. And go ahead and compute again the 4-point amplitude. And this is trivial again, since it's on shell, this term won't contribute at all. So you just have computed from a vertex from these two, which it's over here. And then you have to do all permutations in this case for this amplitude, not only cyclic, because we don't have color anymore. So once you include all permutations, you'll find that the amplitude indeed is STU as the one that we had before. So here is like your simple scalar example of how the double copy works. And now I actually want to stop and make sure that no one has any questions on this or in the previous lecture before I move on to actually start with current research topics, like how to do this in ADS. I see a question.
Mariana, the relation between the Galilean in this, the relation between this special Galilean Lagrangian and the non-linear model Lagrangian is not evident. The phi is not the same. Why is this difference between these two Lagrangians? How you explain this?
Well, in the sense of Lagrangians, I mean, it will be the same with Yang-Mills and gravity, right? The Lagrangians are entirely different.
Yes.
But yes, in the amplitudes, you can see a double copy structure. Some people have tried to build a double copy that's actually obvious in the Lagrangian. And to do that for this scalar case, you actually have to rewrite it in terms of different fields. So you have to pick a different field parametrization that gives you the same scattering amplitudes to make the Lagrangian like obviously as the double copy of the nonlinear sigma model. But it's a different field parametrization for both nonlinear sigma model and this special Galileon. And it not only involves one scalar field, actually it involves several fields. So.
Mariana, can I ask another one?
Yep.
So maybe it's in the line of what Antonio just asked, but in principle, the Lagrangian of the sigma model and the Lagrangian of the Galilean theory, they have very different, even local symmetries, right? They have different symmetries. So these symmetries do not at all influence the amplitudes. Your point is that they will have all the same amplitudes.
So I mean, the nonlinear sigma model has amplitudes that go with a sublimit that go like P, and this is the nonlinear sigma model. And this special Galileon has sublimits that go like P cube. So this is in the sense that the double copy enhances the soft degree. But yes, the symmetries are different. In the sense of, you can think also for Young Mills, I mean, your gauge symmetry is different. It's a UN versus a diffeomorphism.
Okay.
Yeah.
You may want to kick this one to the discussion session. Where these Galilean theories are useful? I know people in cosmology that they become interested on those, but if you want, kick them to the discussion session, and let's move on with the lecture.
Sure. Quick answer, yes, cosmology, they arise in massive gravity theories, but I can tell you more in the discussion. Okay, let me just make sure that there are no more questions before I go to the next part. Okay, so then, oh, by the way, yeah, if you want to see a more non-trivial example, you can check this review, and they do the 5 points, which is slightly more complicated. So let's actually move to the new topics, and it's the new explorations in ADS. So here, the questions I want to ask is basically like, can you generalize this whole construction of the double copy, mostly for Young Mills and gravity? Let's focus on that, for curved spacetimes. And I mean, immediately you could ask a lot of questions. I've been talking only about scattering amplitudes, and defining scattering amplitudes in non-trivial backgrounds that are non-Minkowski is complicated. You cannot define like the same kind of asymptotic states. You cannot use LHC reduction formula. So how do you even construct scattering amplitudes in non-trivial backgrounds? It's a big question. So if you cannot do it for scattering amplitudes, can you do it for correlators? And also, I guess a big if is here. It's on-shell scattering amplitudes that we double copy. So yeah, the question is, okay, can we do it instead for correlators? That's something that we know we can compute. And also the question is, can you do it for classical solutions? So as I told you here, we already know that the answer is yes, although it's not for all of them. So let me put just a yes in highly symmetric cases. So let's first understand what are the two possibilities of doing a double copy in a curved background. So option number one is to consider that the background is fixed. And by that, I mean that both theories, both your gauge field and your graviton, live on the same background. So the background is a curved spacetime, and then you have some sort of Young Mills field living on that curved spacetime. And then when you do the double copy, you keep the background fixed, same curved spacetime, but now you have a perturbation for the graviton living there. And the question in this case is, how do you even define scattering amplitudes? As I said, in these curved backgrounds, depending on the background, you cannot define appropriate asymptotic states. You don't know if you have causality to actually see the evolution of your states, or if the evolution is even unitary, if your spacetime is globally hyperbolic. Like, you could have a lot of issues in just curved backgrounds. So it's only a few backgrounds where you would expect to be able to do this double copy. The second option is to try to double copy both the background and the perturbations that he lives in. So now, instead of assuming that the background for Young Mills is a curved spacetime, you will assume that it's some curved background in the sense of your UN group. So once you have this non-trivial background, you have a perturbation around it. And then when you do the double copy, you will perturb both the background to some curved spacetime and the perturbation. And you expect similar kind of issues in these curved backgrounds, of course. So let me first mention what is the recent progress. And I do believe that this is capturing all the papers that exist on curved backgrounds. So it's not a lot. And if you can see the years, it's very recent. So it started 2017. So 4 years ago, and we don't have a lot of understanding yet of a lot of these problems. So for the case of scattering on non-trivial backgrounds, one of the progress has been looking at plane wave backgrounds. And this is basically by this group of Team Adam over here. So if people are interested, you can look at this. And the reason why you can do plane wave backgrounds is because you can actually define scattering properly there, since they asymptote to flat space. and there's only a non-trivial region where they're curved. That's the reason why you can do this. But it's not maybe very interesting because scattering on a plane wave background doesn't tell you much in some cases. So maybe more interesting thing for this audience is looking at CFT correlators, or I should actually say here in all ADS, because there's been for higher dimensional one. And in this case, there's been a few progress. The 3-point case actually is sort of trivial, similar to the flat space case. So that one's nice and has been done in these papers. Then the 4-point, we already run into trouble. And that's quite sad comparing with like flat space, where we know that it works probably to 5 loops for sure. Here, we can't even do 3 level 4 points. So this is what I'm gonna focus on now. And I'm gonna focus on what's the work of these 2 papers that's similar in spirit to the flat space case, because it works on momentum space. But I also wanna let people know that there's also different approaches to do this in ADS, and there's some people working with Mellin amplitudes where Kinematics duality seems to appear non-trivially and might work, but they also show that the double copy is not reasonable. So there's issues. And there's also a case using the embedding space formalism to compute the correlators. And in that case, your BCJ relations are actually going to be operators instead, so differential equations instead of just the algebraic equations I showed you. And people still also don't know how to do a double copy. So this is literally, we don't know how to actually make double copy work, not even at 4 points. So if anyone ends up with an idea after this, that would be amazing. And I really encourage you to try that. And what I'm going to talk about is actually something that ends up being in momentum space and very similar to what happens in the massive case in flat space, which is also active research. And we also only know a few cases where it works. So besides doing scattering, there's this other case where you can do classical solutions, but I'm probably not going to go there. So I'm not going to focus on that part. So let's actually go and understand what happens with ADS. And let's do this for ADS for amplitudes. As I said, I'm gonna follow these ideas of these 2 papers. And just so you know, if you're gonna go and look at them, what I'm calling here T, they call U. It's a very annoying convention that we mix a lot of T and U definitions all over the place in scattering amplitudes and double copy. So you have to always be careful what's the definition. And the idea is going to be here, as I said, we're going to compute it in momentum space. So we're going to use Witten diagrams. And well, these Witten diagrams give you basically the transverse part of the 3D CFT correlators. I'm going to stay in ADS4 for simplicity. But if I remember right, people check ADS5 and ADS6 too. So now, if you want to think about the analog of what would be your Yang-Mills amplitude, here what we want is the 4-point correlator of these currents that are also charged under this non-abelian UN. And this correlator is going to be my color ordered analog of what I have of my amplitude 1, 2, 3, 4. And just as I had in flat space, instead of just normal Feynman graphs, here we have our Witten diagrams. So for this color ordering, these are going to be the contributions. Again, we have like our standard S channel. Here is going to be our U channel, and you're going to have contact terms. And I mean, I'm going to assume that people are familiar with Witten diagrams, and I'm actually not going to show the explicit expressions because they're complicated and don't really give you any insights. But for those who know, you just construct them with bulk-to-bulk propagators that you can build out of the equations of motion for your Yang-Mills field, and also with bulk-to-boundary propagators. So just some notation. We're going to take this K to be the momentum of each of these particles. So that if I have a Ki, denotes, if I have an I, that denotes which of the external currents it refers to. And it's going to be space-like. And just for convenience, I'm also going to define for D1, that's null, so just the radial part is just going to be the same as the as this k. Now, just like in amplitudes, what you want here when you do the double copy is to understand what are the singularities of your correlators. So when you do the double copy, you can actually reproduce the singularities with the correct residues. So in the amplitudes, you know which ones are the poles and which ones are the residues that you expect. For correlators, it is also understood now what are the expected poles and what are the expected residues. So once we do the double copy, we want to make sure that what we will get is something reasonable, not with correct poles, with correct residues. So in this case, it is known that one of the residues is actually the scattering amplitude in flat space. And the pole is actually when you take the whole energy going to zero, and this energy is just defined as this sum over the ki's over all the momenta of the external particles. So the fact that we have this limit also is what encouraged people to think that, okay, since we have flat space correlators, it's very likely that the same, here you again require these polarizations as usual. I mean, here I'm defining the, this is the 4D one, but you just add an extra zero there, perpendicular as usual to the momentum. And then we define these special Mendelssohn variables. This is basically the analog of the Mendelssohns in flat space. If you're familiar with Witten diagrams, you probably already know all of these kind of computations. And these again are gonna be defined with this 4D momentum just for simplicity, and it's just making the calculations easier. And these, when they have an under bar here, they're defined with respect to the 3D space, like, just so you remember the notation. Is there
probably a stupid question, but you are propagating gravity fields in the bulk, or are these Young-Mills fields?
Right now, Young-Mills, because I'm doing with currents and they're gonna be colored ordered. Okay. Not stupid, I should clarify. Okay. So first I'm gonna start with Young-Mills. And I want to check if we have color kinematics duality. And if we do have color kinematics duality, then I would like to build a double copy. And then I would compare with what I would get from gravitons.
Okay.
So the first step, whenever you want to understand if you can build a double copy, is to start with your theory that has color and see if you have color kinematics duality. And if you have it, then you try to do the double copy. And once you do the double copy, you try to make sure that this is a physical theory. And then you try to understand what this theory is. So yeah, whenever I have these J's, each of these should have an A, B, C, D index for their colors. I'm suppressing them just for simplicity. A lot of times I'm just probably gonna write something like this. But yeah, you should remember all these are currents. So yeah, I'm working with gluons propagating on ADS. Okay. So since these are gluons, again, we're in the adjoint, and the color ordered correlators are literally defined in the same way as the color ordered amplitudes, just by stripping the color, meaning by removing the trace of the generators. That means that basically everything that we had in flat space, all the notation we can again use here. So from the example I showed you before, we have something like this for A, 1, 2, 3, 4 color ordered amplitude. We literally had this expression. And this expression, it wasn't special for the nonlinear sigma model. It's not special for Young-Mills. It's just generic for any color theory in the adjoint. So we have the same literal expression here in terms of this NS and NU that we can write in the BCJ form. So far, I will tell you that this at least looks similar to what you had in flat space, so gives you hope, but let's start to see what is different. So first of all, with the Mendelssohn variables I defined above, so let me, oh yeah, well, they're right there. With these ones, and of course the analog definitions for T and U by exchanging these two for a 3 and U with a 4. So if you do S plus T plus U, what you will find now is that this is the following function and it's non-zero. But of course, if you take the energy to go to 0, which is kind of recovering the flat space limit, then you get that this is 0. If you remember at the beginning of this, I just showed you that S plus T plus U equals 0 was actually important to make the double copy work, to make that matrix that I had to be non-trivial, the one that was relating my amplitudes with my color kinematic, with my kinematic factors. So this was important to make this relationship non-trivial. So the fact that this is not 0 in this case can be problematic, and we'll see how.
Are you may I ask something, Mariana?
Yeah.
Are you normalizing the energy by the radius of the ADS scale? No?
Yes.
Yeah,
Yes.
Okay,
Yes.
thanks.
Yeah. Or setting the radius of the AD scale to 1 if you want.
Exactly. Yeah. Thanks.
Yeah. No, thanks for pointing it out.
No, because I ask it because after probably you will talk about this. No, that sometimes people take the ADS scale you think of as a cutoff, and then they take the radius to infinity and reach flat space results. No?
Yes.
I don't know if you will talk about this. Or, yeah.
Not besides the fact that in those limits things seem to work just like in the flat space, but I'm not really gonna go into detail more about it.
Thanks.
Thank you. So the second difference besides the Mendelssohn sum not being equal to 0 in this case is that we actually don't have color kinematics duality, which is already okay, what are we even doing, right? If you actually went and grab these NS factors and sum them, I'm just gonna call this a Q for simplicity. You will find that this is not 0.
Mariana, can I ask you a question?
Yes.
This is probably some misplaced intuition from my side, but I would expect things to be closer to flat space if you have, if the process is more energetic, not less energetic. If it happens in smaller length scales so that you don't see curvature or whatever.
I guess this comes into what Alejandro was mentioning of the normalization of the energy.
Okay.
Yeah, if you actually include the ADS radius there and you take the ADS radius to infinity, that's when, that's why taking the energy goes to 0 limit, which is actually taking the radius to infinity goes to flat space.
Okay.
This is the normalization issue, yeah.
Thanks.
Yeah, if I give you the notes, I'll actually put the proper normalization just so it's clear. It's just that I guess it's common to use it in the when you write all these correlators just to declutter a little bit your expressions. Maybe before I move on, are there more questions? Okay. So yeah, as I was saying, immediately here you will say, okay, there's no color kinematics duality and there's no hope, and maybe I'll stop. And that's probably what people did for 2-3 years until people figure out what to do with the massive case in flat space. So if you think about this, this is literally like the massive case in flat space. Here, for the massive case in flat space, you have S plus T plus U is equal to 4m squared if all of them have the same masses. And they also find that NS plus NT plus U is going to be different. But what they found is that, surprisingly enough, the fact that this is non-zero actually helps us. This ends up being good because you can recover color kinematics duality. So the same thing that was done for massive case in flat space is now what people did for the curved space case. So let me show you what that is. So basically, the idea is that we have generalized gauge transformations. That is still something you can do. I mean, that was just gauge transformations and field redefinitions. You're still allowed to do that in curve space. You still have both. So those would generically change your kinematic numerators. And as I said before, they change them in the following way. You will define them something like this. And surprisingly here, they save us because you can keep your correlator invariant, but you will actually end up changing what your ns plus nt plus nu is. So if instead of working with this, I work with this tilde version where I shift them by a delta arbitrary function times s, the Mendelssohn variable. So here I will just have the ns plus nt plus nu, and this will be a delta times s plus t plus u, which is in this case this psi. So now I have this delta psi, which gives me the opportunity to pick my arbitrary delta to whatever I want, which in this case could be minus q over xi, because this is going to be equal to q, and then that will go to 0. And I can recover my color kinematics duality. Surprisingly, the fact that your Mandel stems down to 0 allow you to do this very sketchy trick to have kinematic factors that again satisfy the same algebra. And yes, I said this was first noticed in flat space, that you could do it for massive gauge bosons, but here you can do it the same way. But the fact that you can do this and you have this sort of imposed color kinematics duality doesn't tell you that you're going to have a correctable copy, and that's where the problems start. So let's just look at the same kind of matrix that I had before, but now for the correlators. So if you remember, for the partial amplitudes, I had here that partial amplitudes matrix, ns and nu, because now I have actually, well, in this case, I could make them that they have color kinematics duality. But once you look at the matrix over here, you will find that it is invertible, which is completely different from the previous case. If you remember the previous case, this matrix was not invertible. That implied that there were some PCJ relations for the scattering amplitudes that also is related to color kinematics duality. And the fact that you have color kinematics duality allows you to construct the double copy. So here you have sort of a forced color kinematics duality just by this non-trivial way of imposing it, but you don't have BCJ relations, not in the same way as before. So this correlator, instead of satisfying the BCJ relation as before, it satisfies this sort of modified, if you want, BCJ relation. And at that point, you might start asking if things are going to work the same way, because now what you're taking as your scattering amplitudes being your correlators don't have the same relations as before. And as I told you before, if in flat space, if you want to find a theory that actually satisfies color kinematics duality, what you do in practice is graph your BCJ relations and check them. And again, if you take the flat space limit, this would be satisfied, but in the curved space, it's just not. So people so far only found that you have color kinematics duality, but they have no clue about this. So of course, the issues are, what I just told you is that you can shift any kinematic factors to make them satisfy color kinematics duality. So that means that any theory can be double copied in principle, but that again doesn't sound reasonable, because we know in flat space not any theory can be double copied. Another question is if the double copy is even reasonable. And as I said, this is the analog of the massive case, and they have seen that at 5 points, the double copy is actually not reasonable. So there are a lot of issues. By the way, how much time do I have left?
Basically like 10 more minutes for just like lecture, and then 10 minutes for questions. But
okay.
Yeah, there's been some questions throughout, so I don't know if you want to do 15 and 5 or
We'll try to do the 10 and 10. Let's see.
10 and 10? Okay.
Yeah.
I'll let you know then in 10 minutes when it's done.
Sure. Thank you. Okay. So far, this is what was done in these papers. So what I want to do now is try to analyze if this is a correct double copy or not. And so this is not going to be stuff that was done in the papers that I showed you before. This is using this formalism that was developed for the massive case in these papers, but now to understand if you actually have a double copy that's reasonable or not for these correlators. And to do this, it's going to be like, again, a sort of repeating previous stuff, but with a different notation so we can actually understand the issues. And for that, I'm going to basically rewrite all the BCJ double copy in this matrix notation. So the thing that I had before was like a sum of the CI and I over DI that basically can be written in terms of these C vectors, a matrix D and this N. So this matrix D basically has just Mendelssohn variables. If you remember, this color just has traces of generators or structure constants, and N depends on polarization vectors and momenta. Now, for the color kinematics algebra, I can write it in terms of a matrix also applied on these color vectors. So for example, this in the 4-point case would be something like a CS plus CT plus CU. So your C would be just a column vector, CS, CT, and CU, and your M will be a matrix that it's mostly zero, so it only has basically just 3 factors of 1 and everything else is 0. So they're very trivial, but it helps to understand what's happening. And in our case, we have that this generically is not 0. So we're going to start with those. And this will be sort of your expected double copy if you believe with these kinematic factors. But as we said, this doesn't satisfy color kinematic algebra. So what we need to do is now restore this duality. So as I did before, you define this tilde with this delta N shift. So now the first requirement for this delta N shift is that you want this amplitude over here to stay invariant. And here I'm calling it A as the amplitude, but you can also think of it as the correlator that I was talking about before. So you basically plug in your N tilde, and you're going to find that you need this extra factor on delta N to be 0. But since you know that you have the color kinematics algebra for the color factors, you can basically impose that this is just an M transpose times some vector V. So now everything depends on finding this V. And when you find this vector V, you will find this shifts delta N, and then you will say you can do a double copy. So our goal right now is to find V. So this is our goal. So the second thing that you require besides the shift leaving this amplitude or correlator invariant is that it satisfies the color kinematics algebra now for the N tilde. So now you basically put it here in your matrix equation and start expanding things. Now the N tilde, the delta N, now you know that it's defined by this. So here delta N now is V, that's M transpose and that vector V. And we already know that this is equal to that Q that I mentioned, just notation. So this is the basically equation that defines what the vector V that I want is. And you should notice like there's going to be this matrix here. It's going to be block diagonal, and it's only going to have an NJ non-zero components where these are the number of Jacobi identities. Because if you remember, this M is what applies to color kinematics algebra. So it's how many Jacobi identities you have. And similarly, this Q also has only NJ non-zero components. So when you have to invert this matrix, you have to be careful of what are the components that you invert. You only want to invert the non-zero, and you want to see if it's invertible or not. Because remember, our goal was to find what V is. But for now, let's assume everything is fine. You can invert it, and you have now your result for your vector V that you want, which is given in this form. And now we want to look at the double copy. So we grab our double copy now in terms of these n tildes that actually satisfy color kinematics duality after we did this shift. And again, pure algebra. I don't know if it's worth going through it, but basically remember n tilde is going to be now with the shifts. Here, once you put the shifts immediately, oh, by the way, this D is going to be symmetric. So D transpose is equal to D if it ever appears here, for example. You're going to find that the second term here, this with this is immediately 0, just because now our new n tilde actually satisfies color kinematics duality. Then you can expand the first line here over here, and then you'll find that you get the standard term that you will regularly expect for a double copy, but you get this new term with these Qs, which basically measure for like the amount that the original kinematic factors don't satisfy Jacobi. So this is kind of like the breaking of color kinematics duality, gives you this extra term. And then there's also this matrix over here that you require its inverse. So the question now is like, okay, is this a reasonable double copy or not? So let's basically explore that. And if you look at the first term, which is what will happen in a standard case when you have color kinematics by default and you don't have to do any weird shifts, this is perfect. It has the same pulse as Yang-Mills. So it has the energy, total energy pool, and it has these poles that appear. So for example, for the Witten diagram, if I cut this leg over here and I just measure the energy left of this side, then this will be equal to that. And then you'll also have a pole on the energy on the right side. And since you have those poles for Yang-Mills, you also have the same kind of poles if you had gravitons, so everything's fine. And I will be happy with the kind of poles that are appearing here. This will be like basically the standard double copy. All the poles are what they're supposed to be. But then we have this extra part. And this extra part, basically the poles would arise on the inverse of this matrix. So the inverse would basically be the adjoint matrix of here, the aggregate, sorry, and over the determinant. So the poles are given here by whatever you find in the determinant. And in principle, that can contain non-physical poles. So we can go ahead and look at what happens in the 4-point case. So in the 4-point case, this is simply, this M is what I said before, it's just one row of ones, everything else is 0. This D matrix is gonna be just like the Mendelssohn variables S, T, and U, and what you'll find is simply the sum S plus D plus U. And as we know, this was non-zero, we saw it before. This, no problem, we have an energy pole. We know that we want that one. But then we have this extra pole that looks like a spurious pole. That's something that's not physical and problems, of course. Now, this is just a quick analysis I did in the same style as the massive one. So I'm not gonna claim that this definitely doesn't work and that this is a spurious pole. But if this were to work, the only way that it could work is if surprisingly the residue of this pole is 0. So this has to be checked. So you have to compute the aggregate of that matrix and see if it's 0. If it's not, I kind of have a feeling it's probably not, and you don't have a physical double copy. So yeah, I mean, it's not always the case that you get a reasonable double copy, not even at 4 points, because you have poles that you don't expect, and the poles happen because when you shift these numerators to actually satisfy color kinematics duality, you're basically forcing them to satisfy color kinematics duality. You end up adding extra stuff to your double copy, and this extra stuff gives you extra poles, and these extra poles are not necessarily what you want. They can be what you want, but even in this case, you gotta check that the residue is the correct one, because you don't know if the combination of the residue of what's gonna appear here for the energy and what's gonna appear here, it's gonna be the residue that you expect for graviton, 4-point graviton correlators. So there's a lot of questions. It's open research and no one really knows if this works or doesn't work. But this is basically the way you can check. And just as an aside, you can also check this looking at the KLT double copy if someone's interested. And it's a similar idea. You have to do inverse of matrices, and you have to check if the poles that you're getting are the correct poles or not. And there's ways of starting to understand how you can get the correct poles here. So the next part we'll be looking at classical solutions, but we're going to skip that. So I'm just going to go to this little diagram I have for what the double copy is. And basically I showed you for flat space that you can do a double copy to get to gravity. We hope that this also works in non-trivial backgrounds. Big if, I guess, it works for classical solutions at least. So since it works for classical solutions, we'll hope it works for more than that. And it also works in string theory, equals ED equals string, it works for many other different kind of theories with supersymmetry or not. In some cases, again, with mass different from zero in flat space. So yeah, it seems that there's still a lot to do and to understand. So thank you.